Hi there, Nelson again, continuing my science series. I think I'll change the name to Science for All Ages rather than what I had before, because some of the stuff I want to talk about is really what a child can understand, and some of it is what's taught at university, but hopefully it's all helpful. So today I want to talk about size, that size and scale. So for instance, here's a little helicopter. It's a scale model of a Sea King. It's a 1/72nd scale. So that means that the full-size Sea King helicopter is 72 times longer than this, 72 times higher than this, 72 times thicker than this, 72 times rotor blade. You get the idea. It's a question of length. Here's a different scale model. This is a scale model of the aerobatic aircraft, the Pitts Special. This is a 1/8 scale. So the full-sized Pitts Special aerobatic aircraft is 8 times longer, 8 times higher, 8 times wider. But what's really interesting, I think, is how it applies to creatures. Could you have a 1/8 scale or 1/72nd scale horse? A horse which was 72 times shorter, 72 times skinnier, 72 times shorter than a full-sized horse. And what would that mean for the way it lived? Well, it's not what you might think. Take, for example, falling from great heights. Now, falling from heights is quite dangerous for things the size of people, but you might have seen the videos of little ducklings from nests high up in a hole in a tree, and when they hatch they just jump down, and it can be several meters, and people are often amazed how they don't hurt themselves. Well, they wouldn't. It's no problem for things that small. Mice can drop from an aeroplane and not hurt themselves. In fact, any animal up to about the size of a rat can fall from an indefinite height and not be injured. And so we're going to look into a little bit of the reasons why that's actually quite logical and shouldn't be any great surprise. Another really interesting feature of that is the amount of heat energy that animals put out. Now, insects are often thought of as cold-blooded, but they actually put out more heat energy in their little bodies than big animals do. For example, a bumblebee, which admittedly is quite a big insect and it's a very hot kind of insect compared to some, but it's only really because of its size that it gets so warm. If a bumblebee was as big as the engine in a Toyota Corolla, it would get about as hot as the engine in a Toyota Corolla. That is to say, for its volume, it generates about the same amount of heat. So what that tells us, that if you scaled up a bumblebee, or in fact almost any insect, to the size of a Toyota Corolla motor, or to be more relevant, the size of a dog or the size of a sheep, it would get so hot it would cook its insides. And if you scale those things up to a cow, they'd almost catch a light, they'd be so hot. Now, the reasons why big animals can't be that active will become apparent a little later. It has to do with their surface area. Along those lines, a couple of other features of that is that you can't make engines like Corolla engines. So if you take the reverse, if you have a car engine that runs on burning petrol and make it as small as a bumblebee or even as small as a housefly, it wouldn't work because it would cool down so fast it couldn't maintain the heat in its cylinders. There's all kinds of features of that. But what I want to do next, so as not to tell you too many stories, is to give you some things to do. Now, this is the middle part of this video, so if anybody wants to do these things, I suggest when I've said them, you pause the video and write it down, otherwise you might forget. So, one of the things you can do about size is to drop things from a height. Now, if you drop a couple of stones, a big stone and a small stone, from the top of a step ladder or out a window that's high up in a building, they'll reach the ground more or less at the same time. And there was a famous experiment done by Galileo a long time ago from the Leaning Tower of Pisa, where he dropped a cannonball and a small steel ball, and they hit the ground at about the same time. And this has led to the notion that everything falls at the same rate, which is what you get told in physics. And it has an element of truth in it, but it's not really true in a true practical sense. And you can demonstrate this because falling in air and falling in water is actually very similar. So if you get a jug of water and you drop a stone in it, we get to the bottom at a certain rate. If you get a little stone, drop it in, it goes slower. And if you get a really tiny stone, it goes slower still. Now I want you to try that. Try different sized objects of the same general type, like they're all stones or they're all hunks of brick or concrete, and put them in water and look at the rate at which they sink and try and work out how that relates to their size. The reverse thing you can do is to blow bubbles. It's not actually that easy to do, but you can try blowing big bubbles. See how fast they rise to the surface. Almost wants two of you side by side, and I tried, if you get a straw and block the end with blue tack or plasticine and make a couple of pinholes in it, if you're lucky you can blow smaller bubbles. You might want to get somebody standing beside you to watch what you're doing, because you'll find that the size of the bubble affects how fast it rises to the surface. The other thing you can do, but don't use too much of it or else retrieve it, is lumps of butter. Butter floats on water. Try a big lump of butter and a small lump of butter and see how quickly they rise to the surface. So what we're looking at here is the behaviour of different sized objects and the reasons why they behave differently. I should have said earlier too, one of the things about scaling is that people sometimes say if a grasshopper was as big as a person it could jump 200 metres. Well, no, sorry, it couldn't. If a grasshopper was as big as a person it would jump about the same length as a person, and that has to do with the strength of muscles and the weight of their body and similar such things. There's a whole lot of studies that might be worth looking up on the internet about bone thickness in big animals versus small animals, but I'm not going to go into that right here. But what I am going to do is do some really simple arithmetic as to what's going on with big things and small things. So let's take a little box, a little block. Let's say it's 1 centimetre cube. Okay. So we draw a little box like that, 1 centimetre. So what we're looking at here is how much surface has it got, how big is its outside if you like, and how big is its inside. So how many sides has a cube got? Count them up. Can't see them all obviously on a two-dimensional picture, but there's the bottom, the top, the left side, the right side, and one end and the other end. So there's 6 sides, and about a centimetre square each. So the surface is 6. Surface is 6 square centimetres. Okay. What's its volume? That's easy. Volume is 1 cubic centimetre. 1 cubic centimetre. Okay? So next, let's double that. Now what do we mean by double? Make it twice as voluminous or twice as long? Well, we're talking about twice as big in terms of its main size. So now it's 2 blocks high, 2 blocks wide, and 2 blocks deep. Let's get my picture. Have a close look at that. Okay, how many sides, what's the area of its sides? So each side is now 4 squares, 4 square centimetres. And it's got 6 of them, 6 sides. So 4 square centimetres on each side, and 6 sides in total is 2 times 2 times, which is 4, which is 6 sides. 6 fours are 24. So its surface is 24 square centimetres. What's its volume? So if you made that out of blocks, how many blocks would there be? Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 blocks to make that. So its volume is 8 cubic centimetres. Volume 8 cubic centimetres. Okay, so let's do one more. I won't do all the drawings. Just do very briefly, at least I won't do all the calculations. If we double it again, I haven't done this to scale, which is a bit naughty. If you look at that diagram there, okay, so if those squares were the same size as those squares, sorry, I did it a bit small, but that would be twice as high and twice as long and twice as deep as the previous one. Okay, so we've doubled its, what we call its size again. And if we count up all the squares on the surface, they make up to 96. If we count up all the blocks that would take to make that, it would come to 64. Now, if you do the calculations on this, you will find that 6 is 6 times bigger than 1. So the 1 centimetre cube has a surface area to volume 6 times, 6 square centimetres for every cubic centimetre of volume. The next one up, that's 2 centimetres each side, is 24 over divided by 8, so it's got a surface area to volume ratio of 3, and if you do the same number on the 4 centimetre cube, it's now 1.5. So what we are saying in relatively simple arithmetic is that the smaller the object, the more surface it's got for each volume inside it. Now the equivalent is, you might find this a gory comparison, that if you were wanting to make little rugs, you could make them out of rat skins, but if you had, let's compare it with, say, goat skins. Say, what does a goat weigh? Say a goat weighs 30 kilograms and a rat weighs half a kilogram. If you got 30 kilograms of rats and skinned them all, you get a lot more skin than if you skinned one goat. They've got more surface. Another way of looking at it is, if you're a heart beating or the metabolic heat generation inside the muscles of a rat, you've only got about, say, that far to go for that heat to get to the outside, to cool off. If you're making heat inside a goat or a sheep, it's probably that far from the inside to the outside. So the bigger the animal, the more difficult it is to cool down. And that's why things as big as cows can be exhausted or go into heat exhaustion quite easily just by making them run and run and run. And big animals don't tend to be able to run that far. The one animal that can run further than most is actually humans. And that's because we sweat. we're one of the few animals that sweats all over their body. And the other one, which is also known for fast, long-distance running, is horses sweat all over their body. And if they didn't, they would go into heat exhaustion very quickly if you made them go very fast. And humans are able to evaporate water off the surface of their body to stop them going into heat stress when they run for long distances, which probably made the earlier hunters have quite an advantage over some of the prey they were chasing. Okay, so that's enough for now. Remember the instructions earlier on. Try some different, I had said dropping stones in water. Or the other thing you can do is cut up some polystyrene foam and drop it from a tall height. Make some little tiny bits, maybe so big, and have some that are bigger. And look at the rate at which they fall and see if you can understand the difference in terms of their surface area versus their mass. One way of thinking about that is the amount that Mother Earth is pulling them down, the gravity, is proportional to how heavy they are, which is what their volume is. But the air is slowing them down, and that's proportional to how much surface they've got rubbing against the air as they fall through it. And with polystyrene, because the pulling down force is quite weak, the air that they've got to push out of the way to fall is quite significant. Whereas with stones, there's much more mass weight pulling them down, and so the effect of the air only comes into play when they're going very, very fast. Indeed, if you drop stones from aeroplanes, the little ones will end up falling more slowly than the big ones. Anyway, that's enough for now. I'll stop right